In this video, I will show you one of the ways that the inverse Fourier transform is used in the context of data analysis and signal processing. The inverse Fourier transform is a perfect reconstruction of the original measured signal. So you might wonder, what is the point of going from the time domain to the frequency domain, if only to go back to the time domain? One reason is to implement signal processing techniques in the frequency domain. I'm going to discuss this concept in more detail in a later section, but I thought it would be interesting to introduce the idea already here. Here's the idea. Compute the Fourier transform of a signal, change the amplitude or phase values in the frequency domain, and then compute the inverse Fourier transform of that modulated spectrum. This approach is useful only when there are clearly spectrally separable components in the signal. Let me show you an example in MATLAB. Here I create a time domain signal that comprises two components. There's a sine wave at 4 Hz and a sine wave at 10 Hz. Let's say I want to remove the faster part of this signal in order to isolate the slower part of the signal. The idea is that I'm going to compute the Fourier transform, find the coefficient corresponding to 10 Hz, set that coefficient to be 0, and then take the inverse Fourier transform to get back to the time domain. So here I compute the Fourier transform. Here I compute the frequencies. This is code to find the index in the Hertz vector that corresponds to 10 Hertz. This says 14, it should say 10, sorry about that. Once I find that frequency, I can set that frequency index to be 0. Here I compute the inverse Fourier transform. Now notice I'm not using the original Fourier coefficients that I obtained from the forward Fourier transform. Instead, I'm using the modified Fourier coefficients in which one coefficient corresponding to 10 Hertz has been set to 0. So, inverse Fourier transform, and then I plot the original signal, the original Fourier coefficients, and then the reconstructed signal in the time domain. Running this code, you can see what the original signal looks like. There's two components to this signal, a faster component and a slower component. You can see those two components here, so there's one component at 4 Hz and one component at 10 Hz. But now somehow this doesn't look quite right. I was hoping to zero out the 10 Hz frequency, and in fact I did zero out the 10 Hz frequency. But I still see a 10 Hz component in this signal, although it looks smaller than the 10 Hz component in this top signal. So see if you can pause the video, figure out what's going on, and fix it. The problem here is that I did indeed zero out the frequency, but I only zeroed out the positive frequency. That means half the amplitude of the 10 Hz component is still in this spectrum, corresponding to the negative frequency of negative 10 Hz. So what I need to do is also zero out the negative 10 Hz component. So we can do that with this code. So I go to the end of this vector, I subtract off the frequency index that I'm looking for. Now normally when you're indexing like this, you would index end minus this thing plus 1. But now we need to add plus 2 because on the positive frequency side, there's the DC component that we have to skip. And at the negative frequency side, there is no DC component. So now I rerun the code. And now you can see I've completely removed the 10 Hz component of this signal. All I have left is a 4 Hz component. Remember, this is the amplitude spectrum of the original signal. You can plot the amplitude spectrum of the modified signal, and you'll see that indeed this component is 0. This procedure in general is called bandstop filtering. Bandstop because I pick a band, a frequency band, and I stop all of the energy at that frequency. However, one important word of warning. The method that I used here is more for teaching purposes than for real applications. The issue is that zeroing out one single Fourier coefficient can introduce artifacts in the time domain signal. That's not the case here because this is such a simple signal with only two components. For real applications, you would want to have more gentle slopes instead of a hard edge. I'll show why this is the case in the section about the effects of non-stationarities on the power spectrum. You can also see why this procedure is appropriate only for signals that have clearly spectrally separable components. If the two signals overlapped in the frequency domain, then just removing some frequencies is not going to be able to isolate one part of the signal from another part of the signal. In such a situation, you would need to apply a source separation or dimensionality reduction method. If you're interested in learning more about techniques like that, then I can recommend taking my course on dimensionality reduction, which is not yet published but should be available in the next year. So in this video, I showed you an application of using the inverse Fourier transform to suppress a spectral feature of the signal while leaving another feature untouched. This shows the usefulness of the inverse Fourier transform for signal processing applications, in this case, bandstop filtering.